All right. So this work is about training-free open vocabulary attribute detection. So in this work, we want to tackle attribute detection, which is the task of detecting attributes in images for objects. So as you can see, attribute detection is an already explored field of computer vision. But the problem is that to train models for that, you need a lot of training data. You need annotations, which are tricky to get because you have to annotate all the attributes for each object and so on. So we want to overcome this limitation by going training free, so without the need for any training data. And to do that, we want to construct a cache similar to tip adapter and SOSX, which are which are cache-based methods. And the idea is that you build a training-free linear layer using some samples to construct this cache that can guide the prediction at inference time. Now, the idea is that these two methods, which are designed for object classification, they basically get some samples for each class they want to classify, and they construct the cache based on that. But for attribute detection, that's not feasible because you would have to put all the objects and attributes in the cache to make the comparison possible. But if you have like 80 objects and 117 attributes, which is the case for OVAD, your cache basically explodes because you take the cross product of these two. So our intuition is that you don't need all the pairs in the cache to build an informative and actually useful cache. Like for example, a plastic panda doesn't make much sense, so you don't need it in the cache. So the rationale is that we can construct the distributions that model how objects and attributes relate to each other in the real world, and then sample from them the objects that we want to put in the cache. So we use a retrieval database, CC12M in our case by default, and we count the co-occurrences of attributes and objects to get a score. And we do the same with the language model by asking it how much does each attribute apply to each object. And at that point, we can combine the two scores to get these proxy distributions that we can sample from. At this point, we just go through the cache construction mechanism, which is quite similar to tip adapter and SOSX, with the only difference that we introduce soft labels, which means instead of having just one-hot labels, we want to represent the multi-label nature of attributes. And we do that by using clip scores. Now, this may sound silly because we're using clip to annotate data, but clip is also the model we want to improve upon. But that's not an actual problem because we take the one-hot labels and we combine them with clip scores by giving more importance to what we know for sure is in the image and slightly less importance to clip scores. So we basically we can basically choose the level of importance of the two. At that point, we can use the cache as tip adapter and SOSX at test time. And as you can see on both OVAD and VAW, we outperform other cache-based methods, which we adapted like in a naive way to the attribute detection task. But we're also competitive with training-based methods. And as you can see, we come very close to overnet on the OVAD benchmark, which is like the most important and relevant benchmark for the task.